So we've got about half an hour left for module 4. And I'm going to basically launch right into this. It really is a hands-on module. And so, I mean, really, this is sort of where we're going, but really we'll be following the step-by-step guide to do an MDS plot, and then also to calculate some sample intercomparisons. And so I'm going to pull that up, and I'm going to walk through some of those examples with you guys. And I would encourage you at this point to open up DZmds, and we'll work through some of those examples. And yeah, I think it's loading on my machine. Okay. So hopefully everybody was able to download and install the MATLAB code, or the MATLAB compiler, to be able to get DZmds and our other MATLAB-based programs to work. So hopefully you see a plot or a window that looks something similar to what I've got here. And we're going to jump right into calculating a 2D, of course, a 2D MDS plot based on the Kuiper V value. So loading this stuff is super easy. Just click on this select file button and navigate to where you've got your folder, in this case, application 2, MDS software and data, and you're going to load that, that application to uranium-lead ages and uncertainties file. So highlight that, open it, it'll populate this and give you the number of samples that you have. So 11 samples, as we saw in that previous, I think it's actually the same data set that you saw in the slideshow. The input uncertainty is 1 sigma, but it doesn't really matter because we're going to be using the V value. And again, this doesn't really matter either because we're using the V value, and so we're not dealing with probability density plots or kernel density estimates. We're going to be using the metric squared stress, so we'll leave that as it is. We can get the MDS dimensions, and it'll walk through. Essentially, this is the stress value that we would like to, or that we'll get for each of the dimensions that we can plot. Obviously, we're focused here in 2 or 3 dimensions just because we want to be able to visualize this data in Cartesian space. Once you get out to 4 or 5 dimensions, the utility of this method breaks down a little bit, and just that in it's difficult to visualize those 4 or 5 dimensional representations. So we're going to change the number of dimensions. We want to try 2 dimensions, even though that gives us a fairly high stress. So down in number 7, where it says enter the number of dimensions to use in MDS, we're going to put in 2 there. And then click button number 8, plot MDS and shepherd plots. And so that is the shepherd plot that you saw, including the stress that you saw from the PowerPoint presentation, and then also the MDS representation there on the right. Give me just a minute here. We can do the same thing based on changing the number of dimensions to 3. So if we say, well, 0.23 is just too high a stress to be reasonable, to be a reasonable representation of our data, we can bump that up to 3. We can expect an associated drop in the stress, and we can plot that again. Note that the the distances plot closer to the disparities. In our shepherd plot, note that our stress has dropped, and we're also representing that data now in 3 dimensions over on the right. Unfortunately, I haven't yet found a good way of representing this 3-dimensional data or this 3-dimensional plots in a journal, for example. What we need are like interactive journals that you can plot interactive plots like this. But nevertheless, it is phenomenally useful to be able to look at the relationship between these data just in MATLAB or in this GUI, to be able to assess those relationships, right? So if you're looking at one dimension here, it's very difficult to tell that that mixed sample is actually fairly distant from source 7. They look fairly close until you get, some of these other views of how that sample is oriented with relationship to source 7, for example. Let's see. We can so the way that you get this to rotate is this sort of cube button up at the top left. You can also zoom in and zoom out. There's a bunch of functionality that you can do within this GUI, but I'll leave that for now. We can do the same thing using a non-metric stress. So this is the ordinal only. Notice that when we try to use non-metric stress, hopefully you heard that ding, right? So I'm not getting a result, meaning that somewhere, as it's trying to calculate the stress or calculate the MDS for dimensions out to whatever, it's running into a problem, right? So somewhere along here, it's unable to calculate an MDS relationship for non-metric stress with this data set. And probably what that means is that you've got data points that are sitting right on top of each other, that it's unable to sort of pull apart. And so you're going to wind up with an error. And so there are a couple of options. If you get that sort of the ding of death, my recommendation would be, simply try a different stress metric. And that's why we've got 3 here. Again, with this particular data set, non-metric stress doesn't work. Metric stress works to a certain degree, and metric squared stress works to a certain degree. And we can look at some of those other relationships as well. Again, there and there. Let's see. So question from Isaac. My chat did show up. So does it matter which version of DZmds we use? It shouldn't do. I think the only version that we have rolled out on GitHub is the most recent one, which should work well. And that's also the one that was in the Google Drive folder. If you downloaded it from the journal supplementary material, then it's probably been updated since then. But apart from that, I think all of our public versions are consistent. All of these plots can be either exported so that they can be viewed independently, right? And they can also be saved both as plots. So once you export them, you can save individual plots here, and they can be saved as PDFs or vectorized EPS images. But you can also export the MDS scaling after you've done this, and that'll export an Excel file with the X, Y, and maybe Z. If you've done a 3-dimensional MDS, the X, Y, and Z coordinates of each of these points, so that you could take that data and plot it in a separate plotting program. So there's a question here about selecting the file. So to get your data uploaded, you're simply going to go to number 1 up here, select file. Should come up with a browser. The data that I'm using is in the folder that you downloaded from the the Google Drive. So it's that application to DZmds software and data folder, and it is that file there, just the application to uranium, lead ages, and uncertainties. And then again, just open that, and it's already populated it. But if it hadn't populated it, you'd see the path up in here, and then you'd see the number of samples in your Excel file here on the right. And once that's happened, you know that your data has sort of successfully been uploaded. You can start to play around with it. So that's it in terms of DZmds. Again, it's a very useful way of visualizing those dissimilarity matrices, but you shouldn't think that it provides any additional. It's not an additional sort of analytical tool. It doesn't provide any additional objective relationships. All it does is it takes that dissimilarity matrix and it presents it in a way that we, as very visual creatures, tend to be able to interpret it well. I'm going to move on to DZstats. And before I do that, I want to ask if there are questions or anything that people want me to go over with regard to DZmds.
Yeah, there's nothing else in the chat, Joel.
All right, excellent.
So
I'm going to pull up the DZstats. It'll take me a minute here. You guys, I would recommend doing the same so that you can follow along here.
Hey, Joel, I've got a quick question.
Yeah, go ahead. This is Peyton?
Yeah.
Yeah, go ahead, Peyton.
Is there a way to use the 3D interactive MDS like in a, say, in a PowerPoint presentation or something?
Not that I've ever tried. Yeah, I haven't tried that actually. I've tried putting it into journal papers and been unsuccessful. I've not tried using it in a presentation. But as Mark has put into the chat there, you could record a video clip. So there are ways that you could do it in terms of just sort of taking a video of your desktop as you mess around with it.
Right. Okay, thanks.
Isaac, there is not a way to annotate. So the only annotation that's available in DZmds are those arrows that link either the closest samples or the second closest samples. Those are automatic, and the sample labels are automatic. They're pulled from your Excel file as well. Changing colors, all of that stuff. I apologize. I didn't get into that at all. I assumed that people would want to take that and mess around with it in Illustrator. So they're not really publication ready, and I apologize for that. But it's what it is.
Joel, a quick note on, so I've been making a lot of MDS plots lately, and I've stumbled upon something that makes things easier. And so I thought I'd share. So you can save the plots, you can export the plot out of DZmds and save it as an EPS file, which is it's a vector editable image. A better way to do it, what groups things better, is if you go to edit, copy, and then paste that into Adobe Illustrator. It'll group things a little bit better. And the thing that it really does nicely is it doesn't break up some of the text. Joel, I know you've noticed this, how it breaks up the text on the axes. It'll keep those intact if you just go to edit, copy, instead of save and then pasting that whole thing into Illustrator. It's a better way to finalize a figure for a paper or a talk or whatever.
Cool, thanks. So I've gotten DZstats. This is sort of the main window for DZstats, and we'll walk through a couple of examples here. So what I'd like to do sort of first off is, let's see, I guess, why don't we go to probability density plots. We'll go to intersample compare, which we're just going to compare a bunch of samples together. Take a minute for that to pop up, and you can see that file there. So a few of the things that I've pointed out already are xmin, xmax, and xstep, right? So that's the age range that you have to sort of think about, particularly when you're dealing with cross-correlation coefficient. And that's the xstep, so the discretization, again, that you have to think about anytime you're using, for example, similarity, likeness, mismatch, or cross-correlation. Those are going to be relevant things to think about. But we'll pull up our data here. Again, it's just hit that browser button that's there, and it'll take you to the file or the folder where DZstats lives, wherever you downloaded that to. If you go up one level, you should have some data there that we can import. So application 3, uranium-lead ages and uncertainties. Select that and open it. Again, you'll see the path up in this text box, and you can see it's sort of overrun a little bit there. Let's see if I can make that a little bit bigger. There we go. And the number of samples here on the right. I'm going to leave the defaults. So xmin is 1, xmax is 4000, xinterval is as 1. And in order to sort of get that data into the software, we hit plot. And you'll see all of those plotted on top of one another in a manner similar to what Kurt showed in his first presentation. Also the CDFs of all of those. And so we can then come down here, you can look at all of those metrics individually. So that would be the cross-correlation dissimilarity matrix for sample 1 through 11 compared to sample 1 through 11. And we can do the same for, the chaos, for example. That'll pop up another window, and just got that similarity matrix there. You can also run all the tests and export that as a spreadsheet. I'm going to quickly do that. I think it's worthwhile. I think we've got time as well. So I'll call this trash. And why did that not work? Huh. Let me try that again. All right, there we go. So that would be equivalent to sort of pushing all of these buttons, all 5 of them, and copying the data into a spreadsheet. It's just a shortcut, but you can see all of that information, the dissimilarity for all of those samples laid out there. And when we wrote this, we did include the p-value. It's there. You've already heard my take on it, so treat it with appropriate caution. Let's see. That's pretty much it for DZstats. It's a very sort of nuts and bolts, get the data and then do whatever you want with the data for that. You can export those PDPs to a spreadsheet. That's there. It'll just give you, the discretized probabilities as a spreadsheet. You can also export these graphs if you need to. Not sure why you would need to, but that option is there as well. And what Kurt said about being able to copy this into Excel, or sorry, into Illustrator, or save these as EPS files, that applies. Maybe more interesting for DZstats is this subsample compare, and so I'm going to go there next. So this intersample compare takes all of the data within a sample and just compares them to one another. And particularly in our samples, I'll show you here in just a second, our samples are actually quite different in terms of their size. So here's the data that went into that. This is the application 3 uranium lead ages and uncertainties file. Notice that that our sample 1 is quite a bit longer than any of the other ones. All the other ones have 100 age uncertainty pairs. That first sample has 2,000. There are sometimes issues comparing, data sets of extremely different sizes, as this one would be. And so one of the things that Kurt and I came up with is this subsample routine. And I'll pop that up here in just a minute. So let's go to that subsample routine. If you've got this up on your desktop, click that button, and you should come up with a window similar to this. So same deal, we're going to go to the software, or to the folder, and upload that file. Again, the path there and the number of samples there. Some of the same features, so the X range, the X interval, we'll just leave those as the default. The N random subsamples tells you how many grains you're going to take from those samples, and T tells you how many times you're going to do that. So for our samples, let's try 90. So we've got 100 grains. We'll make sure that there's some variability in all of those samples. So out of those 100 grains, we're going to grab 90 of them with replacement, and we're going to do that, I don't know, let's say 100 times, right? And we're going to take 90 grains from each of those samples, make a PDP, compare them to each other, and then do that again 100 times. So we'll plot the first of those. And again, that sort of gets the data uploaded into the GUI. So that would be 1, T equals 1 with N equals 90 from each of those 11 samples. And if we select cross correlation here, we're going to pop up a similar sort of table to what we've seen before. But one of the interesting things here is that, or one of the fun things here is that we get not only the mean cross correlation coefficient, so out of those 100 trials, this would be the mean for comparing sample 2 to sample 1, for example. The mean for comparing sample 2 to sample 3. It gives us the N, so how many grains we took from each sample, and how many trials, how many times we did that. We also get the standard deviation, and so you can start to think about, well, is it significant that that this sample is 0.26 and the difference between another one is 0.25? If our standard deviation is 0.1, probably not. So they're probably sort of within uncertainty. They're very similar. So you can use that to both sort of normalize data sets. Again, if you have data sets of very different sizes, and you can also use it to give yourself a sense of whether or not the differences that you're seeing or that you're calculating between samples is really significant or not. So I'm going to close that. I want to bring up one other issue here, or one other test, which is the KS test. And actually, maybe the way to go here is to actually pull up this step-by-step guide, because I've put this into the end of the step-by-step guide. So if we pull up the KS test and we do an analysis of those, for example, we know that sample 1, which is that mixed sample, is a mixture of samples 2, 4 to 9, and 11. But if we look at the p-value for either the Kuiper test or the KS test, one of those samples, only 9 in this case, yields a p-value of greater than 0.05. For the KS test, samples 3 and 9 have p-values of 0.05. So that'd be down here. So sample 3 and 9. But one of those samples, sample 3, was not mixed into sample 1. And so I bring this up merely as a way of highlighting some of the pitfalls that you might run into with an uncritical application of p-values to intersample comparison, right? In this case, we've gotten both type 1 and type 2 errors, and it's the data, the p-values are almost meaningless in this case. There are some real issues going on. So I think that's about it. I'm almost at time. We've got about 10 minutes left. And I guess I'd like to use that time either for you guys to explore some of your own data sets or to ask questions. So let me know if there are questions based on what we've talked about here, or if you run into problems analyzing your own data sets.
Hey, Joel, just a quick comment. Did you want to show conditional formatting by putting, copying this into Excel and showing putting a color map onto this for ease of interpretation? Yeah,
I guess I hadn't thought of that.
So, I mean, that's typically what I do is as a first go at a data set that I've never seen. That's like step one,
Yeah,
look at the data and quantitatively compare it. And even before MDS, I like to do that. And with the standard deviation, it can be really informative.
So I will do that. So just as a way of sort of a first cut at this data, you can simply take this table, copy it. Let me open an Excel file here. And I'll paste it in here. And going up to the top here to conditional formatting, if you just do something like this, again, this is a cross correlation coefficient, and so we would expect sort of our best correlated samples to be a 1, and so something like this gives you a sense of where we're getting similarity between samples, right? So you can sort of say, well, these guys are by and large more similar than those same samples are to sample 1, 2, 3, or 4. So yeah, again, I think just a first order pass at interpreting these guys, and yeah, pretty useful. I think, is there anything else that you wanted to highlight here, Kurt?
You mentioned the standard deviations if you do the subsampling approach. That's another place where you can identify sample comparisons that might be sample size dependent.
Yeah, so you're thinking basically of something like this.
Looking for big standard deviations versus small.
Yeah. So something like that?
Yeah.
Yeah, okay.
So that'll quickly highlight which ones. I think it really highlights non-uniqueness, really, more than anything.
Yeah. So that's certainly a useful way of thinking about this data. The other thing that I did want to talk about, got just a few minutes left here, is we've talked a lot about PDPs and KDEs in this short course. In DZstats, we have not yet built in a KDE function, and so you sort of have to brute force it a little bit. But in some ways, it's instructive to think about how KDEs are calculated. So if we take that same data set that we've been looking at, so this is the same application 3 uranium-lead ages and uncertainties, and for all of the uncertainties, which would be B, D, E, these are all the age uncertainties. If we simply replace that with 20, so a 20 million year bandwidth in this case, that we can then save that file and that becomes essentially a KDE upload file. So I have now turned these guys into KDEs with a 20 million year bandwidth. I can save that. We'll call that KDE. And then get rid of that. Go over here to DZstats. And let's just do an intersample compare. Plot those guys. So that is the same data that we were looking at, thinking about PDPs. It's the same data as KDEs, and you could run all the same metrics on it, right? The cross correlation, likeness, and similarity. You can do all those things that I talked about. Again, it's a bit of a brute force approach, but it works, and it highlights where KDEs and PDPs are similar and where they differ. All right, so we are right up against time. So on my schedule, we've got a 15-minute break coming up here, and I'm going to hang around. And if there are questions, we can chat about those. But we'll get going at 2:15 with Sam's presentation.
All right, Joel, I got a boogie. I'll be back in an hour after EarthCube.
All right, man. Give him hell.
See ya.
So any questions that you'd like me to address?
Hi, can I ask you a question about some guidelines of interpreting, the values of cross-correlation, likeness, similarity? You address in your paper towards the end, but could you kind of run through it when you can say, well, there's a big chance it's derived from the same parent, versus when you can say, well, probably they were not derived from the same parent?
Yeah, I'm super hesitant about any of that sort of hypothesis testing stuff. So I did put in some guidelines in that paper. I can pull that up just a second here. We can look at the image together. Give me a minute.
I definitely, I agree and see why you would not do that. But I think it's sometimes easy for the reader to see visually, when you make the plot with all the values of cross-correlation likeness, what does that mean? And I think that is the difficulty, making those plots to communicate.
Yeah. So caveat emptor. Be careful when you start to take on this sort of stuff. I guess the way that I thought about it in this paper was that we had a bunch of samples, and we looked at so the least similar subsamples of the same population and the most similar subsamples of different populations. So we looked at subsamples where the metric was telling us that they were the most dissimilar, but we knew that they came from the same population. And we looked at subsamples where the metric was telling us that they were the most the same, but we knew that they were coming from different populations. And we plotted those as these different fields, right? And so what that's showing, or what this plot is showing here, is number of grains from 0 to 1,000 versus the coefficient. So ignore these green lines. It's an empirical sample. Doesn't really matter for now. But part of the point is that as you get to higher and higher sample sizes, it becomes easier and easier to discriminate samples that come from the same versus different populations. And so what you're going to wind up seeing is that samples from the same population are going to sort of occupy this pink zone up here, and samples from different populations are going to occupy this blue zone down here. So does that mean that if I've got 400 grains here and I've got a cross correlation coefficient of 0.7 that they're from the same population? Probably not. I mean, I think I'd be very, very cautious in making that leap. But what it says is maybe it's more likely that they're from the same population than from different populations. Again, I think I was sort of motivated in putting together this figure to come up with some sort of hypothesis test, or at least a hypothesis guideline. But more and more, I've sort of come to the conclusion that that hypothesis testing in detrital geochronology is just a very risky business, and you're as likely to draw incorrect conclusions as you are correct conclusions. And so really the most robust interpretation would be, let's say I have 400 grains and I've got a bunch of samples that string out anywhere from cross correlation coefficients of 0.9 up here down to 0.2. What you can say for sure is, well, these guys up here at 0.9 are a lot more similar and are probably more likely to be drawn from the same population than these guys down here at 0.2. But again, it's a relative comparison rather than an absolute sort of hypothesis test.
Yeah. Okay. Yeah. No, that helps.
Yeah.
Thank you.
Carol, if I can add on that too, I am going to go over sort of a strategy in the next couple of modules here that you could use to try to get an understanding of sort of this stuff that Joel is showing right here, the amount of variability that you might expect in a value of cross correlation under that null hypothesis.
Yeah.
I definitely agree with Joel that when you're comparing large numbers of samples, which we're really apt to do in detrital geochronology, over-reliance on a strict decision criteria for null hypothesis significance tests can really get you into trouble sometimes. I guess I would caution a little differently. I think my opinion is that it's still useful, but you have to go into that exercise knowing that you're going to get some false positives, because that's specifically essentially what you're evaluating with that null hypothesis significance test. But yeah, as Joel points out nicely here, these different methods are going to have sort of different levels of variance with what you would expect in the best fitting values under that null hypothesis. And that is tricky to get an intuition for. And so I will sort of show you some tricks that you can use for that, though we won't really get into a standard tool that's developed.
One of the things that highlights, and we haven't really dwelt on this, but I want to make this really, really clear, is that that any interpretation has got to honor the geologic context, and is almost always posed with an appropriate level of sort of modesty in terms of its confidence, right? None of these metrics make a study on their own. They are one way that we analyze data that sort of collectively we use to build a geological argument.
Yeah. I guess maybe I can use this time to some other question. you know, a lot of the times when we analyze the detrital zircon data, there are like populations that are just so widespread in, for example, North America, like Grenville and Neoproterozoic samples, but there are small populations that are way more important. Do you think there's a way to emphasize this using any similarity measures, or you would kind of stay away from them if that is the case, and it's kind of like geological reality, that most of your samples are dominated by populations that are just not really super characteristic, and that can skew your use. And like particularly, I do a lot of terrain analysis or tectonics and trying to position different terrains, so that becomes kind of difficult using these metrics. I would love to hear your thoughts on that.
Yeah. Go ahead, Sam.
Let me make sure that I understand your question first. You're wondering if there's any strategies for distinguishing data sets where much of the data set is the same, but there's some unique subcomponent of another data set that's unique.
That's correct.
Yeah. Yes. Yeah, I mean, we're going to talk a lot about mixture modeling in the upcoming sections, and that's a type of thing that could certainly be extracted with mixture modeling. One of the, the sort of class of techniques that Joel used to do that subsampling approach in the DZstats is called bootstrapping. And I will show you some examples of using bootstrapping to highlight how much variability you would expect in sample distributions in a sort of exercise in Python next. And you could imagine using bootstrapped estimates of your distributions to really show where there is not overlap in those bootstrap estimates. That is where there's part of a population that even when you account for sort of sampling variability stands out from the other data sets that you're looking at. If you're trying to do that quantitatively with a large number of data sets though, probably something like mixture modeling is going to be the sort of most compact way to extract unique components from complex data sets and show that one sample has a lot more of those than others.
Okay, that sounds great. Thank you.